Okay, so let's continue this class. Today we are already start during this class. I just remember what we talked so far. We talk about neural networks, some important problems there, some general approaches, like tree embedding, some special graphs, and again embedding somehow or decomposing into bounded tree with graphs. Talk about the big networks. Then we came and talk about some important network design problem, in particular clustering like K-center and K-median. We talk about facility location, which is very related to actually, especially K-median. And now we are talking some version of the problem after the facility location, which is connected facility location. This is actually a problem which is interestingly connected to, somehow related to facility location. It is related to a Steiner tree, and it is related to rent or buy. What is the setting that we are considering? You are given a graph G. We mentioned it previous time. I will go to it faster this time. So you are given a graph G, and you have some cost function over the edges, and you have a set of client D is a subset of V. And for each of these guys, say there is a demand, each of these I guys, there is a demand DI. So here in the facility location, we had two things. We had the connection cost and we had the facility cost. To facility opening cost. Here, we don't have the facility opening cost. However, still we want to open some facilities here among these D people. Such that each person goes to the closest, connected to the closest facility. You can consider the version that also have the connection cost, and this is a generalization, but say for now don't have the connection cost. However, we need to also buy a backbone among the facilities. So how much, and when you want to buy an edge, this is the rent or buy. The cost of buying an edge is M times the cost of renting an edge. So this is M times the cost of this. So what is the problem again? So you are given a set of facilities. So you are given this kind of demand things. You want to find a set of facilities if a subset of D. These are the open facilities. And what do we want to minimize for all J belong to set of demands? You want to minimize DJ times their cost to the, you can say it's the metric essentially C to the closest I star J is the closest facility to J. This is the same as facility location that we talked. And J, so it is essentially for each person, you are want to connect it essentially to the closest person. That's the cost that you will pay times the DI. This is the renting cost. And then M times the C of T. What is the C of T? Essentially, T is a Steiner tree that connects these open facilities. These are the open facilities. This is T. And then what is the cost of T? Cost of T is M times like the essentially those edges that you need to buy. M times their renting cost would be their buying cost. So this is called connected facility. It's a famous problem. And here I want to talk about this problem and then talk about group Steiner tree. The randomized algorithm for these algorithms are beautiful. Some of the nicest things essentially. You will see how you can do randomized analysis and essentially randomized rounding, dependent randomized rounding. These are actually beautiful algorithms that exist. So let's see the algorithm here. It is, again, these are like amazing algorithms. And I think this is proof from the book why do they work. So here we are considering LCUV means essentially the minimum distance between V and U. I think this is a metric essentially, according to metrics. So let's see what is the algorithm for this one. And say m is some constant greater than or equal to 1. This is a multiplicative factor that you need to pay. So this is the algorithm, the connected facility location problem. For each j, let me just fill in these guys.
What was the M? What was M?
M is some constant greater or equal to 1. M times the renting cost. The renting cost is just a distance. M times that is the buying cost. For any edge, like it is $1 is the cost, then M is 10. If you pay $10, you can buy that edge. If you buy essentially, then you can put any, that was the whole idea, that because this is the backbone that you are creating. So when you buy these things, then you can send any amount of flow between them. That's essentially the result. So what is the algorithm? So it is, as I mentioned, it is connected. This connected facility location is an interesting problem, which is somehow related to 3 problems: facility location, Steiner tree, and to rent or buy problems that we talk. So what is the algorithm for that? And this is a paper essentially from a stock paper that gives the references there. I think Anupam Gupta, Tim Garden, and Amit Kumar. And it's like 2003. So what is the algorithm? For each j in the demand set, mark it with probability 1 over m. Let m be this d prime be the set of this guys. You construct a minimum Steiner tree on the set d prime slash r, where r is an arbitrary root vertex. I mean, you can consider one of these guys also as a root vertex. Essentially, you create a Steiner tree on d prime. Then for everyone else, you will assign it to the closest facility in F. A beautiful algorithm. Just consider this one with probability 1 over m. You will open some of these guys. This will be the facility. You will buy a Steiner tree for them. Everyone else, you just connect it to the nearest facility. What is the claim? And you know that here we'll talk about the raw approximation for Steiner tree, which is currently 1.39, the best one. So the above algorithm is 2 plus a row of ST, which is essentially would be 3.39, approximation for connected facility location. So let's see the proof essentially. The proof comes from 2 lemmas, but these are beautiful things essentially. And why this algorithm works actually quite interesting. Good. So the first thing is that let's consider, let's Z star. So Z star is C star plus S star. We have an optimal cost solution. So C star is the connection cost, and S star is the Steiner tree cost for the optimum solution. Optimum open something, and then the first claim is that the expected Steiner tree S is at most rho of ST times Z star. So the expected Steiner cost S that we create. How did we create? Again, we were essentially selecting a subset of these guys, D prime. Is probability 1 over m. We're selecting each of them. And then we will open them, and then we create the Steiner tree there. That cost is at most rho of ST times Z star. And Z star already has S star plus Z star. So that is important. So let's see how does it work. And here, okay, so we will say that essentially the expected cost of this optimal Steiner tree is at most Z star. Then we will pay this rho ST to find it actually. But we show that the cost of a Steiner tree, the optimum one is at most Z star. How can we do that? We need to consider the optimum solution and try to massage it such that we can create an Steiner tree here. Let T star so let T star be the Steiner tree in the optimum solution. Correct? So T star is opening some of these guys. Just change the color. So here, what is this one? These are in the optimum, maybe it's also this one. This is the something that connects this one. Yes, Steiner tree that connects. And for each edge, as I mentioned, the cost of that edge to buy is m times its renting cost. It's the same m. So in that sense, this is kind of the uniform rent or buy because this is the same m for all edges. That's the thing that was the non-uniform was different. So you construct the Steiner tree on F, the set of facilities that we have it, like or D prime here, if F is equal to D prime here, like that. For each vertex V belongs to T star, open a facility and connect them using the edges in T star. Good. So, for this one, so this F and T star, or like D prime, this one, they have some intersection. For example, this vertex is the intersection. So how do we do that? We create essentially, we consider this T star. We buy all the edges. Then for any other vertex, which is not here, like for example, this vertex, I will just connect it to the closest vertex here and buy this path. Good. So I buy T star, the cost of that, I will pay S star for that. Then for all others, I will just consider the shortest path from that guy to this tree, and I will just buy that. Good. Now, for the edges in the intersection of essentially F and T, like this guy. So in the intersection of F and T star, I am fine because I've just connected them essentially through T star and I paid the cost S star. What about those guys? Like, for example, this guy that was like here, this guy. That was not essentially in the Steiner. It was not in T star. I needed to buy this path essentially. Good. How much is the cost of this guy to buy this path? Would be the connection cost to this T star, correct? Because that's by definition is the closest one. But I need to pay m times that. However, what is the chance that this guy is selected? Is 1 over m. So essentially, I have 1 over m. This is the one essentially. I have 1 over m that I will select this guy. But in that case, I will pay m times that. But that will cancel out. It would become C star. So essentially, this T star plus this C star, I can pay everything and connect. So I know that Steiner theory on those vertices is at most D star. And then I need to pay rho star. Now the one that it's a little bit more involved is this one. I want to say that the expected, so that's the part that I proved. So now let's see for the other parts. I want to say that the expected connection cost is at most 2 times D star. Good. So let me just clean a little bit this guy. Maybe actually I can just clean it. Good. So again, so let's consider this is the whole graph and say this is D And then for some of these guys, which is F essentially, I will buy this guy. And everyone else, I'm just connecting. So these are the buy edges, heavy edges. These all are just connecting to the closest facilities. So let's see this one. The cost of this guy, really, this guy that I have selected, it is somehow the cost of this are independent from the, so you can essentially connect this guy through any Steiner tree. And that is the part that we have already computed. So for the connection cost, I want to say essentially a different process of this opening these facilities. And you can say it is equivalent. But so note that what do we do? I have some, you can have some order essentially, and this can be an order that I define, but that does not change actually. You can show that any order does not change anything. But I consider a particular order that I will open these facilities. And again, you can say it is equivalent of to that one, but it is even fine to consider this particular order if you change the algorithm. So how do I do that? This is the things essential. Start from one particular vertex V. And since this V can always guess who should be in the Steiner tree. You can try all vertices and say this vertex V should be in the Steiner tree. So that's the one that you, so this is when we say guess one vertex which is in the Steiner tree means that one facility you need to open, and that facility you can guess which one. It means that try all possibilities. So consider a vertex V essentially here, like the first one, which is among this kind of facilities. I want to do this opening facilities in a way that I'm creating essentially the prim's minimum spanning tree. That's actually a beautiful argument. So consider prim's minimum spanning tree algorithm. What does it do? So at any times, this is the algorithm. You are essentially here. You have a set of nodes, and this is the rest of this. And then you are finding essentially the closest vertex among this. These are the vertices S that you have it. This is V minus S, and this is the spanning tree in the whole graph. But again, this is you can see that I want to create a spanning tree on set F. F are those guys that are opening as facilities. Because it is a metric, essentially this one always you can consider it set F that we are considering. Because, how much I pay extra, it would be twice the cost of that Steiner tree. Because minimum spanning tree on F is at most twice the cost of the Steiner tree. And we already discussed about the cost of, so this factor 2 essentially comes from minimum spanning tree, the 2 approximation for a Steiner tree. And this Z star comes from the fact that we know that the cost of a Steiner tree is at most Z star, the previous lemma. However, we need to still show that how much is the connection cost. Good. So I create this essentially this spanning tree on set F through Prim's algorithm. What do I want to say? I want to say in expectation, the connection cost that I will pay is at most the cost of this spanning tree, the minimum spanning tree, and then I am done. If I say the connection cost is at most the cost of this one, this is the 2 approximation for the problem. Would be 2 times the Z star was the cost of the Steiner tree. I am done. Okay, so what is the process? This is the Prim's algorithm. Start an arbitrary vertex V. Let S is equal to V. Now at each step, consider a vertex J belongs to D minus S. Note that here, this F is equal to essentially D prime that I talked, which is essentially a subset of. Good. I will consider a J that this LC of J to S is minimized. Good. Uh, Actually, this one, I need to change it. This would be not Lj of S, Lj of B. B is a subset of S. That I will talk about it. So, and still I need to say, how do I create essentially this selected markers? So, how do I do that? There is this, I mean, lecture notes, there's something that are not precise. That's the thing I need to go to my own notes. But let me say the algorithm here, then we will go for the analysis. Good. So I have two sets. I have set A and set B. With probability 1 over m, I add this vertex to the Steiner tree S so far, paying m times LC of JS. And then I will add this person to set A. Good. Actually, let me just do this one. I think that might be better if I just do that. This is a bit imprecise, so I need to mention that is correct. Okay, so this is actually the correct algorithm that I'm doing that. So I'm going according to the Prim's algorithm. I have T. T is the time essentially, steps. At step T, I have all two sets. Essentially, I have AT and I have BT. I have this property that at any time BT is a subset of AT. So what are AT and BT? At any time, I will consider a vertex, which is, this is the set S essentially that I'm doing it. So in some sense, the set S is equal to AT at any time. Yeah, so maybe I should actually, let's don't say that because it's a bit different. So I have this BT, which is a subset of AT. AT is the set of vertices that I have considered in the order so far. So I consider the vertices according to Prim algorithm. So I have this, start with this vertex V that I guess it is in the solution. So this is the first vertex V. And then I will consider the closest vertex to current this. So I will, with probability 1 over m, I will say that this vertex should be in the facility things, the same way that I generated this one. In this case, this is a vertex, I don't know, W. I will add, I will call it actually, they call it VT. So VT is the vertex at time t. And go one by. So with probability 1 over m, this vertex would be a facility. In that case, I will add this VT to both B and A. So both of them, BT plus 1 and AT plus 1, would be AT union BT. And this would be BT union. In this case, so this is with probability 1 over. this is the case that this guy is selected as the facility. So I will add to both of them. AT is the set of vertices considered for all vertices. BT contains the vertices which are in the facility. Now, this probability 1 minus 1 over m, this person is not a facility. In that case, I will consider BT plus 1 would be equal to BT. And in this case, AT plus 1 is equal to AT union VT. Now, what is the things? What is the, so I mentioned for the first vertex. First vertex V essentially is both in B and A. What about in the next step? Always I will find the closest vertex to BT. Why? Because I want to note that I wanted to create a Steiner a minimum spanning tree on the set of facilities. Because it's a metric, you can always consider the vertex which is closest to the BT, the previous one. Either it will be selected as a new facility that it is essentially the same thing that the Prim's algorithm is working, or it will be not in the Prim, essentially the one of these guys. In that case, that would be AT, but it will be connected to the closest facility in BT set of points. So what do I need to essentially consider it is this one. How much would be the connection cost that I will pay for each vertex? So consider the expected, okay, so let me just delete some parts so that I can just. So again, it is important that, so always I will find this is the current BT. So this is BT. I will find the closest vertex here. So this is the closest to BT. So in this case, either I will go, it goes here with probability 1 over m, or it goes to outside with probability 1 minus 1 over m. If it goes inside, then I will just pay essentially m times the cost of that to buy this guys. Now, how much I do pay for the connection cost? The connection costs are those guys that they are going outside. How much do I pay for them? For those guys, I will pay essentially at that time, I will pay L of VT and BT. That's the connection cost that I need to pay for this. I mean, it might be less than this actually in the actual, but it is at least, is at most. So this is the expected, essentially, this is the cost that I will pay for this one at this time. This is the connection cost that I will pay for. For each of these guys, what is the expected connection? What is the expected cost that I will pay in the spanning tree? That would be, the expected cost would be, with probability 1 over m, it will be in the, selected as a Steiner, like one of these facilities. Then in this case, I will pay m times L of BT and BT. Correct? So for anything, how much do I pay in terms of the connection cost? It is the LVT of BT at both this. This is the cost that I will pay for these guys. For these guys, essentially in the AT, or for each vertex that goes to AT. And how much expected cost I will pay to buy this edge would be 1 over m times m BT of BT. But this is always less than or equal to this. Correct? Because these are just in terms of expectation. So I can take the expectation of the essentially the connection cost. Good. So you can essentially, for those vertices in A that I need to pay that one, the expected, this is at most the expected essentially MST cost. Good. I will just essentially, and this is, I will sum it over all these steps. So it means that the total connection cost that I will pay is at most the expected minimum spanning tree cost.
Or versus in P and in P or all the.
So this is the MST cost essentially in B. But the expected cost, but because this is a random process, the expected cost of this spanning tree would be greater than the expected connection cost. Because I mean, this is you can say that this probability 1 minus 1 over m is going there, but for those vertices that I'm paying this cost, essentially the connection cost, and those connection costs would be for those guys would be less if I pay the connection cost for that. That would be this is probability 1 minus 1 over m I pay, but that actually I can just cancel out. I said I will pay the whole thing for those guys. So I essentially de-randomize that part. For those guys that I'm just paying the connection cost, they are not. Those guys at that time, that it is less than cost of the expected cost in the MST. And as we discussed, this expected cost in the MST is at most twice the, so this is at most, this is less than 2 times, this is less than 2 times Z star, the Steiner tree on this vertices, and this is at most Z star that we had it from the previous. But this is the idea. I mean, this is actually interesting idea that you are doing it in step by step, and you say that this is the cost that I'm paying this. This would be more than the essentially the expected cost. Essentially, the expected cost that I will pay each time for this spanning tree on B, it is greater than the connection cost, greater than what we call the connection. And essentially, I will get this. But this is from this paper. I mean, you can also take a look at it, but that's actually interesting argument. The way that they are doing, that's actually very interesting and non-trivial argument. Probably you might be able to find some other ways to do that, but this is actually interesting thing that you are considering prims, and then from prims, essentially, by changing prim, essentially, you are doing this. You say this happens a lot, that sometimes you generate some kind of random things. When you try to analysis, you are doing that, okay, I will do in a particular order or something like this. And again, for example, this order is something that you can actually run it. So you know what is this order. But you can say that actually, you can do that, even you do it independently, you can always create such a order on them and essentially get this argument goes through. So yes, so this is this is from this paper. So this is this paper of Anupam Gupta, Amit Kumar, and so this is Anupam Gupta, Amit Kumar, and Timra Garden. This paper in the like 2003, that this is the main result. Okay, so let's go. We are finished with this one, connected facility location that contains both of this facility location and a Steiner tree, as well as rent or buy. I want to talk another very interesting result that exists, and this is the state of the art, about the group Steiner tree. So we talked about it before, I mean, but here I want to give essentially simple analysis on this one. The original proof for that, it was very complicated. This is actually a beautiful proof that you can see all the details. So let me just bring this one. Okay, so the group Steiner tree problem. What was the problem? I mentioned it, defined it before. But say you are given an undirected weighted graph G, and these are some subsets of S1 to SP, P groups I have it. These are all subsets of this. You want to find a tree in G that connects at least one vertex from each SSI. So this is the whole graph, and these are some of these S1, S2. Some of them may have intersection. This is, say, S1, S2, this is S3, S4. Yeah. And you want to create a tree. Maybe this is a tree that you create to this one and this one and this one that essentially has the minimum cost. So if all the groups are just size 1, then it is a Steiner tree. And there is a constant factor of 1.39. But if it is the case, the best algorithm that we have it is log n to the 2 times log p. And I want to present this algorithm. So the things essentially, this is the actual proof. The first proof is by Garg, Kanjawad, and Ravi, and nobody has improved. So this is a big open problem. You can show that this problem actually on trees, you cannot get better than log n to the 2 minus epsilon. So there is, even on trees, you cannot get better than this if the whole graph is 3. But it is important whether can we close this gap between these two problems or not. And essentially the log n factor that we are paying more here, because we are using Bartal or FRT, that pays a log n factor, because we need to go from the graphs to the trees. That's a thing that we discussed. Okay, so here we want to prove this one. If G is a tree, as I mentioned, we are paying log n for Bartal to do that. Rooted at R and depth H. So depth essentially, so this is the root R. And the depth of this one, or the height, whatever you will consider, it is H. Then we can find a solution of cost at most H times log P more than the optimum solution. And here we have H times log P. This is another thing that I need to say for Bartal or FRT. You can actually, the way that you do it, you can make sure that the depths of these trees would be log n. Actually, you can easily get log delta if you remember, because delta was the maximum distance, because each time we are essentially halving the delta. But you can say that actually you can get a stronger thing than log n as well. If delta is, the idea is that either delta is polynomial in n, which log n and log delta is the same. Delta is the diameter in the metric. Either they are the same polynomial in n, which is the same. If not, actually, you can say that you can generally those cases that the diameter is like exponential in this one, it's that the other edges are not important, and you can just do some delta thing because that all are much smaller, and just essentially only the weights of the high orders are important here, and the others are just low order. That's somehow the idea. So you can get essentially log n. So you know that the depth or the height of these trees from Bartal would be log n. So if you are proving this, we are done. So we say that if we want to prove that if G is a tree rooted at R at depth H, then we can find a polynomial time algorithm for this that is H times polylog P. Now, essentially here, the issue that this is, you need to get these 3 things. You will pick this log n more. And then you know that H is at most log n as most. So it would be log n times H, which is log n again, times log P, which would be log n to the 2 times P. This is the one that I have. So I only need to get it essentially for trees. And that's essentially the thing that Kanjawat and Ravi is doing. So this is the idea. So if you want to improve over this, you need to do it somehow. You don't need to do Bartal. So Bartal, for some problem, you can show that you can avoid Bartal in somehow inside the proof, use it as a white box, not a black box. and then improve this log n. Don't pay it. For group Steiner, we don't know any solution like that. It might be possible, but we don't know. This is a very important problem, open problem, that can we get essentially log n to the 2 or log n times like p. Good. So let me just close this one, and then we can go for this other things. Now, this is also a beautiful algorithm, essentially. So let's consider this problem. Let's write an LP. So the LP is somehow similar to this kind of multi-commodity buyout box thing. It is similar to that. But here we have essentially a tree. So what is the tree problem? So the tree problem, you can consider, always you can say this is the tree of root R. You can always consider these S1s, S2, S3, these are among the leaves. This is without loss of generality, because if some vertex is not a leaf, you can just add another vertex to that. So if this is not a leaf and in the middle, then add another vertex and put the cost of this 0. If this was V, then put it V prime. So in any group that V was there, put V prime instead. So you can assume that these are all the leaves, essentially. So all the leaves are in the groups, and these groups, of course, each vertex, each leaf may have several colors. You can consider each of these groups as a color, like color 1 to P, and one vertex can be different color, can have several colors. So the idea is that you want to create some tree here that essentially has at least one from each of us. So what is the LP for this one? The LP would be this one. So you minimize the cost of E x of E. X of E is the same thing that we always had. X of E means buy that age E. Because you need to find the tree, so X of E equal to 1, you buy. So then this is this one. Then we need to use the concept of essentially, for each group, I need to support a flow on the set of buy edges. Always I have this one, that any flow. So for each group, I will run a separate flow, essentially. And what is the idea is that if this is one vertex here, so if this is the group, say Si, I need to send a flow of 1 to this guy, because 1 essentially should have a 1 path here. So it means that I need to send a flow of 1 from R to each group, essentially. That's essentially the LP that I'm writing. So I will say that FG for each group here, FRG essentially is the flow that I'm supporting to this one. On each edge, the flow that you can go is at most the time that you buy it. Now, this is essentially the flow preservation at each vertex. When I get from a vertex, when it comes to this vertex V, some flow, then it should be divided among its children. So that should be the sum of the children. Flow should be equal to the parent, the one that comes from this. I will define essentially f g of v. This is just for each vertex. I will say how much flow is the flow that comes from the parent edge. So you can consider for each vertex and for each edge there is a essentially flow. I mean, you can probably remove those with vertices. There is no need to do that, but you can have it. So for each vertex here, I will say what is the flow that comes to it. This is the flow of the edge that comes from the parent of this guy. So the flow of this V is equal to the flow of the, so flow of V is equal to flow of E, where E is essentially from E to parent of V. And then, of course, one important thing, if this is the important thing, if for a vertex, if this V does not belong to the group G, the flow that goes to this vertex should be 0. This is the additional thing that I do. And that I can just put 0. And of course, it is integral sense. This is exactly this Steiner tree, because for each of them you want to buy such that you can send, and each of them is either 0 or 1. The flow of 1 means that there should be a path from essentially from root to one vertex in F. And you want to buy the set of edges. So does it make sense? So that's essentially the flow argument that I have it for this problem. And this is the way, so I can just relax this. So how do I relax it? I will say that all these x's are between 0 and 1. So I will just relax this LP to just say everything is this, and I will get a solution to this LP, which is opt star, which is at most opt. You have this assumption also. This is also interesting that x of e, you can say that it's always x of e is less than x prime of e, where e prime is a descendant of e. Because whenever you go down, you don't need, because the flow goes down. So at most, how much you buy an edge to the maximum flow. But the flow up was less than the flow down. So always if one edge is here, the flow of that, and this guy is just coming here, the flow of this guy, x of e prime is less than x of e. Good. So that's these things. Now, okay. So I have obtained this one. So what can I do now here? This is the interesting part. So far I have not done anything. Essentially, I have just run this LP, and this LP I have just give me the things that I want. So this okay. So one algorithm, this is like generally when you are getting an LP, how can you run it? One way is essentially consider, for example, some threshold below this, you will make it essentially 0. Above this threshold, you will make it 1. This is one way. You can do the randomized way as well. So you see that I will consider each edge. So this is the edges here are x's. I will do with probability. So xe with probability xe, if it is becomes 1, otherwise it becomes 0. Sometimes you will multiply this one by log n to get concentration or something like this. That we have done it, for example, for set cover. But it is according proportional to x. However, in this case, for Steiner tree, this type of thing does not work. Why? If you consider this one, for example, this guys, this is the essentially you will put it 1/2 here. If you want to consider each edge independently, you will round it with probability xe. Then essentially with high probability, if the length of this guy is essentially h, the probability that this guy is connected to this would be 2 to the minus h. Because each of them is probability 1/2. To make a path from this guy to this guy, all of them should be connected. Each of them is probability 1/2 will be connected, so it would be 1/2 to the 2 essentially minus h, and you have 2 paths essentially here. But at the same time, I mean, so here, if you want to do it independently, it does not. However, the idea is that you need to do some kind of dependent rounding, and this is the very beautiful algorithm. Actually, you can do it. This is one of the most beautiful things that it exists essentially for. One of the beautiful dependent rounding that exists. Again, the original analysis was very complicated. This is a simplified one. I think that's the first one that is presented here. I'm not so sure that these things that I gave it essentially to Marek, and Marek has written it essentially. That's the thing from there. But that's the only source that I know it is formally written. So that's essentially the things. Then the question is that how do we want to round it? So what was the idea? The idea is that if you round this guy, one of this guy to 1, then you should continue on this guy to make it 1. And essentially, in that case, so essentially either you will get this guy essentially one, or you will get one of these passes essentially. Like with probability 1/2, you will choose here or 1/2 there. But this is the dependent, because then if you guys select this one, then you select this one, select this one, select all of them. There is some dependency. They are not independent. Okay, so this is the algorithm. This is the randomized process that we are actually doing here. And that is the beautiful thing. So consider the following randomized algorithm. So initially we place one particle or token at root R. So we put a token at root R here. Then for each child V of the root R, independently we buy the edge RV with probability XRV. So this is for root R. So you can actually consider for the root R here, this is the root R here. You can consider this, actually this, you may consider this root R, put another root R prime before that, and say that this, since essentially the cost of this edge is 0, and X of E of this guy is equal to 1. That's the way, if you consider this way, then you can say actually it's more generally for X. X E of this guy is 1, so its R prime is always coming to R, and you want to connect R prime. So here, say in that case, so this is R. So this is one particle here at root R. With probability, so each edge has some X. With that probability, I will buy this edge. So it might be the case that this particle, it turns out to be a few particles now. Because each of them independently I will buy. So I will buy an edge when we place a particle in B. It is in that this is independent. So I may create actually buy several of them. Somewhere of it. Now we will proceed in a similar way in a top-down manner. Now, if there is a particle here, then among these guys, I will buy one of these edges. Good. And not one of them, may more than that. If there is no particle here, then I don't continue. But what is the probability here that I will buy? And that's the thing that I mentioned. You can consider root is another one. In general, the probability that I will buy is this one. X of E over X of V to the parent of V. So here, what is so essentially, if this is the X of E here, so this is called, consider this is, so this is X of E. And this is, I mean, it can be 1 here, but it's not necessarily 1. So here I have X of E here, and I have X of E prime here. I will do it with probability X of E prime over X of E. With that probability, and as I mentioned, X of E prime, I know that is less than or equal to X of E. With this probability, I will buy this edge. Now, if you add this edge essentially for the root, that would be also the same thing, because this guy has the X of E is equal to 1. So essentially means that would be X of E over 1 would be the same. So this is important. When I have it, these are some of these edges. Each edge I will buy it with probability X of E prime over the X of E. E is the parent of this vertex. Now, what do I want? The part which is easy is this one. So this part is easy. Let me just delete this one. which is easy is this one. The expected cost of my solution, the expected cost of the 3 bought by the above this one is at most up to start, the LP solution. Why? We can prove by induction that for each node V not equal to R, the probability that a particle reaches V is equal to X E of this guy. If I prove that, then I am done. Why? Because this is essentially the probability that I will buy this one is equal to exactly X of these guys. So X of these guys times the cost of those edges would be exactly the optimum solution for the LP. The LP was exactly this one. Cost of edge times X of. Now, why do I have it essentially? So this is actually the induction here is at the depth. So if V is at depth 1, the lemma holds correctly. Essentially, this is, as I mentioned, you can add even this vertex V becomes the root. So depth is from here. So the depth of the root is say 1. Because as I mentioned, why it is 1? Because I have added one other vertex that has the X is equal to 1. So I prove by, okay, so for the vertex root is correct. Now what about for this one? So for V at depth 1, the lemma is false. So now for lower guys, the probability that a vertex reaches V is equal to the probability that this article reaches the parent of V times the that from the parent comes to this. So by induction, I know that this is equal to essentially X of pair of V, pair of V. And then times essentially, this is the probability that I'm putting this new particle or token. So this cancels out, so this becomes this. So that's the important one. So I know that each edge will, this probability XEI will buy it, and because of the linearity of expectation, the lemma follows. Now, that's the first part. That was the easy part. Now, let me actually clear everything. Good. Now, the second part, what do I want to say? Let SG be an arbitrary group for any node V at depth I. So consider this essentially, consider V here. So consider this V, which is at depth I. So here essentially from the root, the depth of the length of the path is I. So it is at depth I. And depth is from the top, height from the bottom. So if this is the vertex B, and such that the XV of the, so some essentially from this, there is, this one is non-zero. The probability that a node from a group SG gets connected to V, assuming that there is a particle at V, is, so there is SG. SG part of SG, I mean, this V essentially, the subtree is this is SG, it connects some part of it. The probability that some vertex from this SG is hit by this process that we have done it is this one. If G of V is exactly the flow that comes through this V, the flow that it is less than the X of V, over H minus I plus 1 X parent of V. Good. Now, if you consider the root, for the root, what will happen? So for the root, actually, you can say that here the depth of the root is equal to say 0 here, or 1 depending on that one. Then here the X parent of this guy would be 1, because from the root we defined this was a special case that what there is the flow F is 1 here, and the XE is equal to 1. So both of these guys would be 1 essentially, will cancel out. And then the only thing it would be 1 over H or H plus 1, doesn't matter. So it means that from the root R, the probability that at least one vertex from SG gets connected to this one is 1 over H plus 1. Good. Say if we are proving this one, this is essentially the heart of the proof. But then what can we say after that? What is the algorithm? So this is the algorithm that I'm doing it. So I will repeat the randomized algorithm that I have mentioned above. So this essentially is particle things. So I will start it with this probability. I will do that. I will create something. I will repeat this one, H plus 1 times like P. Then the probability that a group will not connect it to R, because I know that in each, and I will buy all these H's, the union of all of them. How much do I pay? I will pay H plus 1 times like P times opt star. I'm paying that. Now, what is the chance that one vertex from this group is not connected? It would be 1 minus 1 over H plus 1 to the H plus 1 like P. Because each of them is not connected, would be 1 minus 1 over H plus 1 to this time that I'm doing it. It would be e to the like minus P, it is 1 over P. So I will do this one. If for one group, I have, now, still there might be some essentially vertex that is some group that is still not connected, but that probability would be at most 1 over P. Good. Now, if it is the case for those guys, for those that are not connected, I will buy the shortest path essentially from that to this. It is at most opt star. The shortest path from the root to this vertex, this guy that is not connected, would be at most opt star. I will add that one. But then how much do I pay? I will pay H plus 1 times like P times opt star plus for P vertices, each of them with probability 1 over P is not connected, I need to pay opt star. But this was essentially another opt. So the whole thing would be H of like P times opt. That was in the tree, as I mentioned. If you use the Bartal, you will get another log n because of this distortion. And the depth of this would be log n. So you get log n to the 2 like P, the one that I. So I'm done, essentially. Now let's just prove this lemma, and then we are essentially done. This is the whole idea. Good. So proving the lemma by induction, that is actually the beautiful thing that you can do. You will prove by induction on H minus I plus 1. In the previous time, if you remember, the base case was the root. Here, the base case would be the leaf. So in the base case, consider V is the leaf here. If V is the leaf, then this we said that we want to say the probability is at least this one. Good. If V is the leaf, then if G of V is greater than 0, I know that V should belong to a CGF. Correct? So if a particle is there, then of course that particle covers this one with probability 1. Because if G of V is greater than 0. So of course 1 is greater than this, so I'm done. So here I'm proving for the leaf first. Now, assume that now I consider a non-leaf vertex V here. I proved this one, the induction or induction, I will prove for the children of V. Now I want to come essentially prove it for V by induction. So let PV be the probability that the group SG is not connected to V, assuming a particle reaching at V. So PV is the probability that is not connected. So this V, again, if a particle is there, you will continue these things, and it connects. Maybe this is essentially this SG guys that has some intersection. P is the probability that is not connected. And of course, 1 minus PV would be the probability that is connected. So let's just write math, and essentially we are done with it. Like a beautiful proof, actually, very simple. The original one is much more complicated. The whole thing is this math. So let's just write it down and we are done, essentially. Good. What is the PV? The probability that V is not connected is that, of course, is that it should be not connected. None of these guys that the particle goes there, it should connect it to SG. So that would be, you need to multiply this one, essentially. So what is the, for each V prime, which is a child, what is the probability that is not connected? So this probability essentially, so that would be what is the probability that is connected? The probability that is connected, it would be xe over x parent of V. That's the thing that this particle, if it is there, it comes here. Times the probability that is connected. What is the probability that is connected? 1 minus PV of. I want to get the probability it is not connected. I add this 1 minus. So this is the sum that I try to essentially to get for PV. Now, by induction hypothesis, I just replace this one instead of this. So this 1 minus PV, I just replace it with this one that I had, this one. Okay, so this was the probability that was connected. So it would be f of g prime, g v prime, h minus e times x. Now, what do I do here? So here, I just cancel these things. So because this xe is canceled with these guys, so I just write this one would be 1 minus f of gv prime h of minus e x parent of v. Now, this is the beautiful. This is actually comes a lot that we are doing this kind of analysis. This is the product of this one. To do the product, we can do it. We are using this formula. We will using e to the x, essentially. We have this formula. 1 minus x is e to the minus x. It is a very common trick, such that we can essentially do these multiplications. So I will just use this formula. I will put all of them instead of these multiplications. This is essentially this multiplication. It turns to e to the summations. So I will make it e to the summations. Now, when I make e to the summations, I can now sum it up. This is the preservation flow for a vertex V. When you say that the flow is coming here, it should be divided between its children, and it is equal. So sum over all of this would be sum of this FG. Now, this one, I just change it. I will just change this one. I will put it minus 1 here. This exp of h minus I x parent of this over fg of v. Now I'm using the reverse formula essentially to this is the somehow reverse formula for this. I will say e to the 1. So you can just say this one essentially e to the minus 1 over 1 minus x is less than 1 minus 1 over x. These two are equal. So what is this one? Here I have e to the minus 1, and this is 1 minus x. Here I need to add essentially this one. Here essentially I need to add, sorry, actually this one I need to, yes. So here I need to add the plus 1 and minus 1 here. So this 1 minus this property would be this. So that would be essentially the x that I'm using it. I'm using this formula, then it becomes 1 minus this. This is the plus 1. I got it from this plus. Good. Now, what do I do? So when I have this one, then I will write this one. So I can just write this one, 1 minus this. So this fg of v, and this plus 1, essentially, I can just write this one. That this would be this. That would be essentially f g of v over f g of v. So then this f g of v is going to the nominators. And then I have this guy, essentially this plus this guy. That would be at most, the f of g is at most x of parent of this guy. So I get a plus 1 here. So here I didn't. So essentially I have the plus 1 here. This plus 1 turns into this plus 1. And here I'm using the fact that f is less than x. So I get this one. So what do I get? So here I get this one. So this is the P of V. Now this probability that is not connected. What is the probability that is connected would be at least this one, which is the one, this one essentially got canceled. It becomes f of g over this. And as I mentioned, the analysis for the root is exactly, you will add it and then you are done. So this is a beautiful, essentially line, just a few set of math that you can prove it. And that is the simplest one that I know that, and I think that's the only place that I know that is actually presented. I don't know any other place that is presented. The people may knew it, but not written it, but this is the written. And this is a beautiful thing for the group Steiner tree. Actually, you can get it. And this is the best solution that we have it for group Steiner. As I mentioned, for directed Steiner tree, which is a generalization of group Steiner tree, we don't even have polylog. We have n to the epsilon for any epsilon. We don't know whether polylog is possible. That's another big open problem. Directed Steiner tree. In the directed Steiner tree, so directed Steiner tree is that, I mean, you want to connect essentially these guys from root to a set of these things. Here, then that would be easy. These groups, it will be very easy to make it. A directed, it is a Steiner tree. This is directed, not directed group Steiner tree. Directed Steiner tree is more general than group Steiner tree. Why? Because essentially you just can consider this problem for each of these SG. You can just connect essentially to this vertex. And this is the directed things that you are putting it. So you will say that connect from this. This is, so for each group, you are putting essentially a new vertex. And all of these vertices in this group, you will just connect it by directed edges. And it is important to be directed. If it is undirected, then you cannot go, you can go up and connect these guys, that there is no such thing. But if it is directed, it is one way, you cannot go back. So directed Steiner tree is more general than group Steiner tree. But that we have n to the epsilon for any small epsilon. That's the best thing that we know. This is a big open problem whether polylog is possible or not. Anyhow, I stop here and I think we will continue in the next two sessions about iterative rounding. This is another very general approach for network design that we will talk in the next two sessions. Okay, so talk to you.